All right, we started in chapter 4 last time. I'd like to continue with that. One of the first thing I want to look at is a voltage notation. There are two notations used. One is a single subscript, such as V as A, is used to measure a voltage at any point in a given circuit with respect to the ground. So the single subscript is to measure with respect to the ground. Double subscript is used to measure a voltage at any point in a circuit with respect to another point in the circuit, such as VAB. That means the voltage at A with respect to point B. The first subscript is always at a higher potential, so the voltage V of A, that means put a voltmeter with a positive polarity at point A and a negative polarity at point B to measure that voltage. So is A, the point A is always at a higher potential with respect to point B. And the same thing with the current IAB, that means the current that flows from A to B is a positive current. So A, the first subscript, is always a reference. It's primarily used in a three-phase system. In the three-phase, usually you have 4 lines coming in. You have 3 line to neutral, and then you also have line-to-line voltages. There's a lot of technology going into that, why you want to do that, but at this point, we just look at the voltage notation. Those of you who continue with in electronics and a power system, then you can learn about the three-phase and double notations, line to neutral, line-to-line voltages, and so forth in a three-phase system. But sometimes even single-phase, if you're not measuring a voltage with respect to the ground, you always use double subscripts. So if the second subscript is missing, that means you're measuring with respect to the ground potential. Let's look at an example. Let's say you have a following circuit. You got a 12-volt source is hooked up to 24K ohm resistor, 4K and 10K. Is a simple circuit. Is a series circuit with the 3 different resistors. Let's call this point down here as a ground, as a reference, and call this point A, call this point B. We want to make the following measurements. We want to calculate the voltage V sub A, V sub B, and also VAB. So we're going to look at the voltage from A to the ground, B to the ground, and the voltage from A to B. Now, as a single series circuit, we're going to use a KVL, the summation of all voltages, algebraic sum of all the voltages in a closed loop is equal to 0. So if we start at loop number 1, and I'm going to call this current I, you get a single current that's going through the whole circuit. Going to start from 0 here, minus to plus. By notation that we use, that's a positive potential. Minus, everything else will be negative because the current is always entering the positive polarity of the resistor or load. So plus to minus is minus. So it'll be 24 kilo ohms times the current I. Same thing here, 4K, that'd be minus 4K times the current I, and then minus 10K times the current I has to be equal to 0. Well, if you simplify that, take combine all this, 24, 4, and that gives you 38 kilo ohms, and the current I would be 12 divided by 38 volts, simply 12 over 38 milliamps. The voltage at point B with respect to the ground, that means put a voltmeter here with a positive polarity hooked up to the point B and a negative polarity hooked up to the terminal ground here, which is the voltage across that 10K ohm resistor. So in order to calculate that, you're just going to take the current I multiplied by 10K. So that'd be 12 over 38K times 10K. K and K will cancel out, so you got 120 over 38. That's about 3.1578 volts. If you look at loop number 2, if you don't see it, you can always form a closed loop by putting a voltmeter there. if I'm going to start up from this corner and go in a clockwise, so you got minus to plus, that gives you plus V sub m. And again, that's a plus minus, so it'd be minus entering the negative terminals, go from minus to plus. That'll also be 24, that'd be positive 24k times I. And then plus to minus, that's negative 12 volts, has to be equal to 0. Now, the voltage V sub m is equal to V sub A. That's exactly what you're doing. You're measuring the voltage from point A to 0. So replace V sub m, the voltmeters, with the voltage V sub A. So it'll be 12 volts minus 24k times I. And we got a 24k, the current I was 12 over 38k. K and K will cancel out. So V sub A then would be equal to 12 minus this, which is minus 7.5789. That gives you 4.4211. Now, by definition, when you do a double subscript, the V sub AB, that means V sub A minus V sub A. This is always true for the double subscript notations. V sub A will calculate to be 4.421, and V sub B was 3.1578, and if you do that, it gives you 1.2633 volts. Or we could have said that V sub AB is equal to the voltage across that 4K ohm resistor. So take the 4K ohms and multiply by the current I. It should give you the same answer. So it'll be 12 over 38K, that was the current, multiplied by 4K. K and K will cancel out. 48 over 38, it should really give you the same thing that we had here. Those are all the examples that I want to work out. We're going to set up problems, homework problem, chapter 4, 5, 9, 13, 17, 23, 25, 29, 33, 43, and 49, and then 61. I'd like to go over some of these today, and then we'll assign them for you to turn it in sometime next week. So let's look at the first problem, problem 4-5, which is on pages 122. It says determine the potentiometer setting required in figure 437A, which is this figure right here. So that's a pot symbol they use for the potentiometer with the 3 terminals. And this one right here is a sliding one. You can slide it up and down to provide a total resistance of 52K. So that should be really simple problem. R total will be equal to R1 plus R2 plus R3 settings, and if you want that to be 52K, then you can determine what R sub 3 is. That's what you need to put your pot setting as a. When they have the resistor or the pot like that with the parentheses, whatever's inside the parentheses, that's a maximum resistance value for the pot. That means if your third arm is all the way up here, that is going to give you a short circuit. If it's down here, then you're not shorting out any part of the potentiometers, so the entire pot will be connected in series with R2. So if you come up with a value greater than 10K, then I need to go back and recheck your calculations, because the maximum you can get is 10K out of that pot potentiometer. So the pot has to be at 7K in order to give you a total of 52K ohms. So one problem is 9. It says to calculate the total current for the circuit shown in figure 438C. And this is what they have. You got 1 volt source, 51 ohms, 39 ohms, and 10 ohms. And simplest way is just to calculate the current. You're going to take the total voltage, which is 1 volt, divided by the total resistance combined, or you can use, if you want to use a Kirchhoff voltage law, starting from this corner, minus plus, that gives you 1 volt positive, and everything else would be positive, plus minus, plus minus, plus minus would be negative potential drop. You go from positive polarity to negative polarity is the drop in the potential. Well, either way, it really gives you the same thing. So it would be 51 plus 39 plus 10, that's 80, 90, 100. 1 divided by 100 is 0.01 amp or 10 milliamps. Problem number 13. It says determine the potentiometer setting needed to set a current in figure 439C to 560 microamps. So first, by having you have the voltage, you require 560 microamps, so you can calculate the total resistance. And then from there, just like problem 4 or 5, if you have a total resistance, then you can determine the pot setting or the value of R2. So the current I would be equal to 12 divided by 6.8K plus R2 plus 11K. R2 we need to determine. It's not equal to 5K, that's just the total pot setting. The current is 560 micro, that's 10 to the minus 6. It has to be equal to 12 divided by 6.8K plus R2 plus 11K. Solve for this quantity right here. So it would be 12 divided by 560 times 10 to the minus 6. 1 over 10 to the minus 6 is plus 10 to the minus 6 on top. So it would be 12 times 10 to the 6 divided by 560. Or R2 plus 6.8K plus 11K has to be equal to, if you calculate this, I wrote 10 to the 6 as 10 to the 3 times K, so it'll give you this value in kilo ohms. So 12,000 divided by 560, it is 21.428 K. And so from here you can solve for the value of R2, which is 21.428 minus 17.8 total. That gives you 3.628 kilo ohms. Next problem, problem 423. It's on the bottom of page 123. It says, write the Kirchhoff voltage law equation in the circuit shown in figure 442A to verify that the voltage adds up to 0. So you got 3 resistors. You put a voltmeter across each one of them. The first one reads 7 volts. This one reads with that polarity plus or minus 2 volts, and this one reads plus or minus 6. And it's hooked up to the 15 volt source. So if we go around the loop in the clockwise direction, you start from this corner, minus to plus, that's plus 15, plus minus is minus 7, plus minus is minus 2, plus minus is minus 6. Okay. So if you go around the loop, if you hit a positive polarity, it's negative. And if you hit a negative polarity, it's positive. This is exactly opposite. Some textbook, they use conventional, not actual current flow. So if you go from plus to minus, that means the current is going from negative to positive terminal. And then when you hit negative terminal, that's considered minus. When you hit a positive polarity, it's considered to be positive. But either way, as long as you stick with it, it doesn't matter which way you do it. So 7 plus 2 plus 6, that gives you 15, so it's minus 15. 15 and 15 will cancel out. Problem 33. It says repeat problem 31 for the circuit shown in figure 445C. And this is what I have, the 445C. It has 30 volt source hooked up to 1.1K, 3.9K, and 10K ohm resistors. And problem 31, it says use a voltage divider equation to calculate the voltage across each resistors. So we're interested and the voltage V1, V2, and V3 across the three resistors and that with that polarity. Now we talked about a voltage divider rule. If you had two resistors connected in series, this is what we use. We came up with this equation: V1 would be equal to the total voltage times resistance R1 divided by R1 plus R2. If you got more than two, if you got three or more, then V of X is equal to V of S times R of X divided by R total. So if you apply it for this problem here, if you're interested in voltage across the resistor R1, V1 then would be equal to the total voltage, 30 volts, times R1 divided by R total. But R total is equal to 1.1, 3.9, that gives you 5 plus 10 is 15. Okay. So the voltage across the resistor R1 will be 30 volts times 1.1 K divided by 15K. If you calculate that, it gives you about 2.2. The voltage V2 will be 30 volts. R2 is 3.9 K. The R total stays the same. So 30 divided by 15 is 2. K and K will cancel out. 2 times 3.9 is 7.8 volts. And the last one, V3 is equal to the total voltage times R3, 10K divided by 15. And again, that's 2K and K will cancel, give you 20 volts. And if you add them all up, it should all add up to 30 volts. Or you can just combine those two. That was 7 as 10 minus 30. It gives you V sub 3 to be equal to 20 volts. Problem 43. It says calculate the maximum possible value for the load power of circuits shown in figure 448A. This is what they have in figure 433A. We talked about this. We said with the exception of power applications, if you want to do maximum power transfer to your load, then you match the impedance. Looking back from your terminal of your load, looking back with this short-circuited, you want to see the same resistance. It's called matched impedance. So the maximum power transfer, in this case, R of L setting has to be equal to R of S. The resistance of the source is 15 ohms, so you need to let R of L to be equal to 15. Now, when you do the maximum power transfer, the voltage is, if there's nothing else is hooked up to it, it will be half of the voltage. Or you can just simply use the voltage divider rule. The VR of the L, let's see, B43 says, want to calculate the maximum power. So R of the L, now once you set the value of R of L, then you can use the voltage divider rule to calculate the voltage across the load, or you can calculate the current, then to calculate the power you do I square R, whatever you're comfortable with. There's a number of ways you could do it. But if I calculate the voltage across the load using the voltage divider rule, then you have 8 volts is total times 15 divided by 15 plus 5, which is 50%. It's going to drop across the load. Then you got a voltage, you got a resistor, you have V square or R to calculate the power, and that's the maximum power because you set R of L to be equal to R of S, which is 1.006 watts. Now for the efficiency, maximum efficiency, R of L has to be much greater than R of S. So if you're designing a generator, you really want to make sure the internal resistance or the winding of your armature is much smaller than the resistance of the load. Because if you look at this, you got only have 50% efficiency because 50% of the power will be dissipated inside the resistor, outside the load, or internal resistance of your source, which is not really efficient, but it does give you a maximum power transfer. Problem 61. fast problem there. It says determine the value of V of S3. So you have a source here, it's unknown. That's Vs1 is 12, Vs2 is 20 volts, Vs3 is unknown. But you have you got a voltmeter across a 2.2 kilo ohms that measures 4.4 volts with that polarity. So as soon as you have one voltage here across any given resistor, then you can calculate how much current is flowing through that circuit, because it's a series circuit, current to all the elements would be the same. So the current I would be simply VR3 divided by R3, and that's 4.4 divided by 2.2, that's 2, because of K it gives you milliamps. And once you have the current I, then if you go around the loop, you're going to start off from this corner on the left, minus 2 plus, that's 12 volts. The current is flowing in that direction, because I already determined the direction of current flow. So that'd be plus minus, plus minus, plus minus, and then plus minus. So all the resistors will have negative value. There's a voltage drop across each one of them. 1.1K times the current I minus 1K times the current I minus 20 volts. And then here we had plus minus, that's also minus. But the polarity for V sub S3 is minus plus. You're heading the negative terminal, that's exact opposite, so it'd be plus. And then of course 4.7K is negative, times the current I has to be equal to 0. You can factor out I for all of them. So it'll be 12, current I, 1.1, 1K, 2.2K, and 4.K. Then you get left with minus 20, and then plus V of S3 has to be equal to 0. Everything here, it gives you 9K. Current I is 2 milli. 9K and milli will cancel out. Just simply give you 2 times 9. So V sub S3 then would be equal to, take everything to the other side of the equation, 30 plus 20 plus 18, and then minus 12. It gives you 26 volts. Those are all the problems that I wanted to cover in chapter 4, but I'd like to work out a couple more examples. Let's say you have 24 volts is hooked up to 3 resistors, but you put a wattmeter in the last resistor, number 3, and that wattmeter is reading 24 watts. Resistance R1 and R2 are known, but you want to determine what the value of resistance R3 is unknown. Now, since the power is given here, then we need to look at the power of the input. Power of the source is equal to power of the load. So whatever the source is putting in, it has to be dissipated inside those 3 resistors. So P of the source is equal to P1 plus P2 plus P3, or V of S. The power for the source is equal to V of S times the current I, and V of S is 24 times I. The power for the resistance R1 is I squared times R1, which is 2, and for R2 is I squared times 4. But P3 is already given, that's 24 watts. You got 2I squared plus 4I squared give you 6I squared plus 24, has to be equal to 24I. Take to the other side of the equation, let it be equal to 0. When you do that, you always make the coefficient of the highest power, in this case is second power, to make it equal to 1. So divide both sides of the equation by 6. 24 divided by 6 is minus 4. 24 divided by 4, divided by 6 is 4. Now you get a quadratic. You can either factor it out, you got two numbers. If you add them, you get -4. If you multiply them, you get +4. So they has to be, they got to be 2 and 2. -2 minus 2 gives you -4. -2 times -2 gives you +4. If you don't see it to factor it out, you can always use a quadratic. If you got ax squared plus bx plus c is equal to 0, then x1 and 2 would be minus b plus or minus b squared minus 4ac divided by 2a. So we could do it that way. Now that we have the current I, we have the power for the third resistor. So use the equation I squared R, and from here you can determine what R3 is. So R3 has to be 6 ohms. So sometimes you need to see what's given in the problem and be able to set it up to use the right equation to calculate the unknown. In the second example, let's say you have a simple circuit like this. Got a 24 volt. You have a load here. When you measure it with that polarity, it gives you 10 volts. But you got a resistance R1 here. It's unknown. But you want to measure the voltage across it. And the same thing here. This resistance R2 is unknown. You want to measure that voltage. So if you got a closed loop with one voltage is missing, you can always do Kirchhoff voltage law. So if I look at loop number 1, going to start from this corner, -2 plus, going to go around that clockwise direction. -2 plus is plus 24. Plus 2 minus is minus 10. And then plus minus is minus V1. That has to be equal to 0. So from here you can determine what V1 is. Take V1 to the other side of the equation, gives you plus V1. 24 minus 10, it gives you 14 volts. For loop number 2, you're going to do the same thing. This one is known, this one is known. You can determine the unknown. So if you started out from this corner right here, you go around the loop, -2 plus, that's positive 10 volts. Plus minus is given the problem with that polarities. Plus to minus is minus, and then -2 plus is also positive. So you got 10 plus. So you can see if you are on the loop, you always hit the negative terminals for both, so they be an additive mode. So the V2 has to be equal to 18 volts. Alright, those are all the problems that I wanted to do in chapter 4. We'll stop here, and next week we'll start in chapter 5. That's on parallel circuit. Please take a look at those problems. If you have any questions, email me or give me a call. I'll be happy to go over them next time in the lecture. Thanks.